Welcome again from my side. So the purpose of this hands-on session is to familiarize you a bit with the HPC system we have here, to get you logged on, to train you a bit to navigate around, right, through the command line, and to submit some simple jobs to the cluster and see how one generally sort of to understand sort of the workflow of how one works in an HPC environment. So that's what I mean here with this term cluster computing, okay? So by the end of this first part of the hands-on, you should be able to, if you have your own code that you want to run in parallel, right, that you should know sort of how to build up a script, submit it to the cluster, run it, and get some results out. The second part, this GPU programming introduction, is then sort of building upon that, where we will learn a bit how to program for these special devices that also Simone mentioned, which are very common now on HPC systems, which are these graphics processing units, right? So there we will go a bit lower level and understand some of the basics of how one programs these as I said, devices. Right. So for those of you who are already familiar with a Linux system or logging into servers, etc., then part might not be so interesting, okay? But the idea is to get a so that then we can move on to the sort of GPU programming introduction that comes next, okay? All right, so I'll start, right, so that's my outline. Cluster computing, I want to cover navigating the HPC cluster, submitting jobs, and how you can sort of change the environment a bit with this module system that I will cover. And then introduction to GPU programming will cover the outline of the GPU architecture, main differences from the CPU, and then an introductory sort of example just to understand the basics of programming GPUs. So the assumptions I'm making here about your background, just to be clear, is that you have some familiarity with C or C++, so you sort of can read it at least, or another similar low-level language, that you have some dexterity, let's say, with the command line, like, CDing into directories, etc., although we'll cover it a bit. And also that you can edit text files on a remote server, either using a text editor there or something like VS Code remote. So even though I assume this last bit here, then if this is the first time you're doing this, it might not be so important that you are very comfortable with this. We'll cover a bit of the basics together. Okay, so ways of accessing the slides. So I recommend you do it as I showed you before I started changing laptops here, which is to access the slides directly, because then you can, it's easier to copy paste code from the slides if they're in a browser rather than a PDF. But if you really want, then for this training session, we have set up this GitHub repository. So if you navigate to GitHub and go to the user CaSToRC-CYI, that's the user, and then the repository for this training event is ncc-training- and the year month, so 2024-03. And maybe it's worth then doing this now. So if I click on that, then that takes me directly here, as I said, CaSToRC-CYI/NCC-training-202403. So this is the repo for this training session. You want to go to slides, and then there are two PDFs there. That's Simone's introductory PDF from before, and this is what I'm covering now as a PDF. But as I said, I recommend you use browser. The exercises are 3 exercises that you don't need to worry about now. I will tell you when we will need these as we go along, but they're also there if you want to get them, you know, when you go home and want to, I don't know, review what we did today. Okay. Okay, everything clear up to here? Stop me at any time, yeah? I'll try to go slow, but sometimes I get carried away. So you should bring this to my attention when I do. Right, so cluster computing. So here is a very bird's eye view of what we will be logging into and using, okay? So this is a cluster or an HPC system with, and there are, well, I'll stay here because I need to point with this, you can see the pointer, right? Okay, so this is where you want to run your jobs, the compute nodes, okay? These are servers. You can think of them as servers. Each one of these boxes that I've drawn here to represent a server as a CPU, as memory, as a network card, right? It has its own sort of network interface. It has a GPU in our case, right? Or GPUs, etc. So there's multiple of these. So you can think of one of these as what you think of as a computer, as one computer, right? One of these is like one computer. They're all stacked together in a rack, and they're all connected together through a network, okay? Not necessarily TCP IP, right? Could be InfiniBand or, you know, some special network, but in any case, they're networked together. They can talk to each other. Okay, so what you see as a user usually is not these compute nodes, right? As a user, you log in to so-called login nodes. They're drawn there. In our case, there's one login node. Bigger systems might have multiple login nodes. But when you connect to an HPC system, you are dropped in to a specific node where you're not supposed to run jobs, okay? You're not supposed to run programs on a login node, right? So you land when you connect, when you SSH to a cluster, you land on a login node. Sometimes they're called front-end nodes. They used to be called master nodes, but we don't use those kind of words anymore, right? Right. So you drop into that, and then from there you launch jobs on one or more compute nodes. Okay. And this is the workflow. If you're not familiar with this, this is why you're here, because this is what we want to do in this first introductory part of the code. Okay, so what did I not cover is that there's also a storage usually, which is, you can think of it as more of these servers, but just connected to big disks, right? It's just that I didn't draw it like this. And in an HPC system, all the nodes see a common storage, right? So if an HPC system is set up as is typically of such systems, then there is somewhere a network attached storage, which is visible, the same storage, the same files, folders, hierarchy, etc., is visible to all compute nodes. So it doesn't matter which compute node you're on, you can see all your files, etc., in the same way as you would if you were on the login node. Okay, so some specific things about the system that we will connect to today, okay? So we will connect to our Cyclone system. That's the name of the system, which is something like 100 or more nodes, compute nodes, okay? But we won't worry about all the different 100 nodes because they're different architectures and different, different projects running on the same, on different nodes, etc. So that they vary. But what I will restrict to is 2 nodes that we have reserved for this training. They have specific host names. The host names are GPU03 and GPU04. So they are the host names of 2 of these boxes that we will be using, right? And they are called GPU03 and GPU04 because they're equipped with GPUs, right? They have GPUs on them. So they have 2 20-core Intel Xeon processors, each 186 gigabytes of memory, and each has 4 of these data center GPUs, Volta architecture data center GPUs, and each GPU has 32 gigabytes of graphics memory each. Okay, the other thing that we will be using is a common storage for this training event, which if you if you were created an account through the registration process, you will have access to this dedicated space, which is under /nvme/scratch/edu19. edu19 is the name of the project that you have all been assigned to because you're part of this training event, okay? When you make a project like Simone, I explained before, so you apply, you get a different project name, and that is the name of the, usually the name of the storage that you access is under that kind of directory, etc., etc. Okay. So, that's something I already said. You log in. The workflow is you log into the system, which drops you on one of these login nodes, right? In our case, there's just one, so we don't have to worry about them being more. It's just one node that you drop into, which is one front-end node, login node. In our case, this has the name front02 because it's front-end node. And then to run programs on compute nodes, you use what we call a job scheduler. Okay. And we will be here distinguishing between interactive jobs and batch jobs. So let me just explain what I mean here by a job scheduler. So let's just imagine now that this was a very primitive system where you just had connected nodes, right? So you log in, you drop onto a login node, and now you want to run a job, okay? So in a system which would not be set up, let's say, for an HPC environment, the most straightforward thing to do was, once you're on the login node, just connect to one of these compute nodes and start running, okay? And that would work fine as long as there's not a lot of users on the system, because then it becomes difficult to know who's running on which node, right? I mean, probably this is obvious once you start imagining what happens when you have many users. So we need to use a special software, this job scheduler, which keeps track of who is running on each node or nodes, right? It's like a reservation system, right? It's called a job scheduler. So in order to use this system, that means that we also allocate nodes, we reserve nodes via this system. And then this software, which is running on all the nodes, just keeps track, right? So that this user is running on these nodes, the other users are running on those nodes. It knows if all the nodes are full, in which case you have to wait. It knows if some nodes are free, which means it can assign them to you, etc. Okay, so that's what we mean by we will be using a job scheduler. Okay, and most HPC systems, this is now become a standard, this so-called Slurm job scheduler. There are different kinds of schedulers available. You might go on an HPC system which has a PBS scheduler. Other systems might have, I don't know, IBM's version of a scheduler. But these days, the most common one is the one we also use here, which is called the Slurm job scheduler. What this means is that the commands you actually type have a specific name, right? But all job schedulers sort of follow the same kind of logic, that there's a command for allocating a node, a command for listing the jobs, there's a command for submitting a job, and there's a command for running a job. And we will cover what the distinction between these is. So if you go to a system which doesn't have a Slurm's job scheduler, these commands will be different, but the idea is the same, right? There's just different commands for doing these different things. Okay, this is where I want you to actually connect to the system. So I will make this a bit smaller. Oops, what did I do? There. I'll make this a bit smaller and put it to the side if you don't mind, and so that I can bring in a terminal. A fresh terminal. There it is. Ah, you don't see it. Just a second. Oh. Okay. Move this into the screen. There it is. I'll make the text a bit bigger for you. Is that okay for everybody in the back? Can you read the terminal? You can read the terminal. Good. Okay. So here I am. Now I'm on my local system. I'm not logged into the cluster yet. And I need you to connect. This is, you all said you already connected, so there's no excuses. You should be able to connect now. Okay. And you see this nice message, so that there is no doubt now that you're actually on a system called Cyclone. So is everybody here? Is everybody here? Yes, excellent. It'll get harder, I promise, but okay, so far so good. So you should have gotten instructions about this. Okay, so as you can see, we are on the front end node, right? This is what I was talking about back here. We are on one of these login nodes. The host name of this login node is front02. It says it here in the prompt, but you can also make it say it by typing the command hostname. Hostname is just a command which tells you the host name of the server you're running. So if I type hostname, it says front02. So far, so no surprises there. So this is the login node. Okay. Now, we can ask for one node. We can ask for one compute node. We do this through the Slurm job scheduler, okay? So we cannot just, from here, SSH to GPU03. I told you GPU03 is one of the compute nodes that are available to us for this training. You can't just from here, just decide to log on to a different node, okay? That won't work. What you need to do is you need to reserve this node through the job scheduler, and then the job scheduler gives you this node, and then you are dropped onto this node. So I will do it here. Okay. And before I hit enter, I want to explain to you what the different options are. So salloc, this means the S is because this is a command of the Slurm job scheduler. So it starts with an S. And then alloc means allocate to me some resources. -N1. So the big N means one node. You want to allocate one node. The -P means from which partition you want this node, right? So on the system, there are different partitions. A partition is just a group of nodes. So there's a partition called GPU. It's the name somebody gave to a group of nodes which all start with a host name GPU, right? There are other partitions on the system. We won't worry about those, but our the nodes that we want to use are part of the GPU partition. And then the reservation is just the name of a hold that's been placed on these two nodes from 9 to 2 today, because we have this training event. Okay, so nobody's allowed to run on the nodes that are under this reservation, except from us, because we want them to be available for this training event. And then this minus big A edu19, you might or might not need to specify this. I am part of many projects on this cluster, so I have, many accounts on this cluster, which means that I need to specify to Slurm which project I want to charge. I mean, not really charging anything, but which project I would otherwise charge in order to use these nodes. And so that's why I'm saying, for the purposes of this job that I'm going to ask for now, treat me as if I'm part of the edu19 project. You are all part of the edu19 project too. You might also be part of other projects. If you are part of other projects, then you will need to specify this. If you're only part of the edu19 project, right? If you're just here for this training, then you can probably omit this, and it will be the default project. Okay, let's see. So, waiting for resource configuration. Nodes GPU 03 ready for job. Okay, and as you can see now, I am on GPU 03. I can tell because my prompt has changed to GPU 03, but also I can type hostname, and now I see I'm on GPU 03. Okay, so I have been allocated GPU 03, and I have been dropped onto GPU 03. Okay, so going back to the slides, this is just repeating what I said. And okay, so I mean, yeah, maybe this is clear, but it's just incidental here that the reservation and project name are the same name. Okay, this doesn't need to be the case. Okay, now I am going to right. So I'm going to exit from this node now. Okay, so I'm going to either type exit, or shorthand is Control D, the same as exit, Control D. There it is. And you see that Slurm tells me relinquishing the job allocation 409713. That's just the number of the job. And now I've exited from the node. Yeah. Okay. So for that brief period between this salloc command and when I typed exit, I held this node, right? As a user, this user here, Koutsou, was holding the node GPU 03, right? Okay. In principle, you don't want to do that because, I mean, I did this to show you, right? But what you hold a node like this, then you are not letting other people use the node, right? So you might think, okay, let me allocate the node, right? Something like this. Okay, now put a script to run. Some script. There's not some script here, but something like this. I press enter, and then I go away. The job finishes, but you're still holding the node, right? Right. Ideally, you want to release the node as soon as you're done running on the node, right? So right now, I'm holding the node and I'm just talking to you, right? And I'm holding the node from somebody else, for example. Okay. So what you want to use is, I mean, salloc is good for debugging, let's say, or testing things, right? If you want to, try something else. But usually what you want to do is just use srun, okay? So on this system, the way srun is set up is, it's the same syntax as salloc, but at the end you add a command, right? So what happens is, when I type, so this this line here is the same as what I had before with the CyLOC. It's just that at the end, I put the command hostname. You remember what we did before? We did CyLOC, we were dropped on the node, we typed hostname, it gave us the hostname, and then we hit Control D and exited, right? This command does those 3 steps in one go, okay? So it CyLOCs the node, it runs hostname, and as soon as hostname finishes, it drops you out of it exits the node, okay? So let's see what this does. Okay, see, so this here is the same as what CyLOC told me before, right? So first it's queued and waiting for the resources. Then I was allocate resources, so this is part of CyLOC. Then it runs the command at the end of the srun command, which was hostname. And then when hostname finishes, which is immediately because it's a very fast job, right? Hostname. It just drops me back to the front end. Okay. So I'll be using srun here so that I don't hold nodes unnecessarily, right? And because we only have 2 nodes and there's like 10 or so of us, if I were to salloc a node and keep it, that would hold somebody from you from using it. Okay. So again, what this does is allocates a node, runs the specified command, in this case host name, and then exits the node, releasing the allocation immediately. Okay. So the output, which when I was writing the slides was GPU02, but when I run it here was GPU03. The output reveals that we were allocated, in our case, GPU03 for this really short job, which was just run hostname. Okay, so you can run multiple instances of the program that you put here at the end. Okay, so let's say I want to run 2 instances of this. Then you can use the -n option, right? So this, what I write here is, this here, command line. Okay, so what this does is, it says use 1 node, but use 2 processes. And what this does is it runs hostname. Again, this is a very simple program that I'm using here for demonstration purposes. But if you're a bit imaginative, you can think of running a more complicated code there instead of hostname, right? Like, I don't know, something that produces something a bit more interesting than just the hostname. But anyway, here what I'm using is hostname, and what I see is twice GPU03. So this program hostname was run on 2 threads, if you want, processes. Doesn't really matter what they were, but whatever it was, it ran in parallel and gave me GPU03, GPU03. Okay, I can go further. I can run 2 processes like I did before, but specify that I want to use 2 nodes, 2 different nodes. Okay, so that means run 2 processes on 2 nodes. So hopefully it will run one on one node and the other on the other node. I mean, there's no way to slice it really. And this might take some time because the other node is asleep. So it might take a few minutes, a few seconds to come to be awake. But I should get now 2 different host names when I do this, because I specified that I want to run on 2 different nodes. By the way, Giriagi, whenever you want to stop me for a break. 11, okay. Okay. So maybe this is a good point that I go around and see if you have actually tried this. Who has tried this as I was going on? Okay. Okay, you should all try this and make sure that you understand what's going on, yeah? While the other node wakes up. Yes. Ah, sure, yeah. Yeah. No, it's 2 processes in total. Two. No, 2 processes in total. That's what that means. Ah, if you write small n4, you mean 4 processes in total, 2 nodes, but it doesn't necessarily mean it'll do 2, 2. It might do 1, 3, right? Yes, but there is a way to force it to do 2, 2. There is a way to do this. We will talk. Is there a way to? Usually, like if it's interactive, then you can usually Control C cancels them. If it's not, then it depends on how you started it, I guess. So if it's a Slurm job that you're running, then you can use S cancel to stop that job. Okay. So this so finally the other node woke up, right? So if I do this again now, this should be faster because the other node is woken up. There it is. So I told it to run 2 processes, 2 tasks, I guess, is what the Slurm terminology is. 2 tasks on 2 nodes. So it put one on one node and one on the other node. You can try different things. Like, I mean, we only have 2 nodes in the reservation, so this won't work for more than 2 nodes, but you could do something like 6 tasks on 2 nodes and see what happens. So if I ask for 6 tasks on 2 nodes, the way it's set up, it doesn't have to be this way. It depends on how it was set up. The way it's set up here is that it puts 5 on the first node and then the 6th one on the other one. So if you want to load balance them, then you need to do something special. We will see what that is. But in any case, you can see what that does. It also stops you from doing silly things. So if I do something like this, then it says can't run one process on 2 nodes, setting in nodes to 1. Okay, so I try to run one task on 2 nodes, and it tells me that it's going to set this minus n to 1 by itself. Okay, so you can also count on it on doing the obvious thing. You can yeah. So you can play with this a bit and see what you get, but in general, you can get up to, what did I do here? Yeah. So you can go up to, I guess, there's 2 nodes and there's 40 cores on each node. So probably I should be able to do 80. Yeah, that works. So if I do 80, then I should be getting 23s and 24s. That's correct. I can count them. So that's 80 lines. And let me see. Okay, they're not in order, so I just have to trust me that there's 43s and 43s and 40 as GPU 04s there. And if it's hyper-threaded, then I could, in principle, also 160. No, it doesn't let me do that. Okay, so I guess I can go up to 80. Yes, 81. It says not enough. 80, it works. Okay. So, yeah. So that covers sort of running how we actually allocate a node, run something on it, and then That's a good question. So there's probably a way to do it here on the command line, but I would have to look it up, to be honest. I don't know off the top of my head how to show the resources, but usually, and this is also the case here, the HPC side has documentation that tells you sort of what these, what the architecture of these nodes are, which also includes how much memory it has, which is not something we cover here, right? How many cores per node, how many GPUs per node, so that you know, and other limitations like what the longest job size can be. Sometimes it can be 24 hours, sometimes it can be 48 hours, sometimes it can be 12 hours. So that's also something you need to know before you design your job. And as I was saying, this is usually available to you on the documentation of the HPC side. Show partition GPU like this. Okay, right. Okay, thanks, Simone. So Simone gave us the command. So it's scontrol show partition GPU in this case. This gives us some information like the max time that you can run on that means 1 day, so 24 hours. What does this say? What does this say? What else here is? Total CPUs is 640, total nodes is 16. So I guess if you divide this by this, you get the number of CPUs per node. What's that? As a total memory, where's total memory? How would you know that? Yeah, no, yeah. So like this, yeah. Yeah. Okay. Yeah, so that's, I guess that answers the question. Right. Thank you. Okay, so let me just say a last thing and then we go for a break. Yeah. So not a last thing, but just something additional before we go for a break. So just to set up for the first exercise, so I would like you to also, just to be able to get a bit comfortable with the command line, I'd like you to make a directory EuroCC training. I think I already have this directory, so it's going to complain, yes. Okay, but if you type that, then you will make a subdirectory under your home directory called EuroCC training. Then you cc into it, cd into it. Okay. And you should have nothing there. Actually, why don't I just do that so that you can follow, so I can follow. So make dir EuroCC training or anything else you want to call it, right? Okay, and then if I cd into it, it should be empty. And now, okay, just so this, I mean, you might be familiar with all this if you're comfortable with the command line, but maybe I should cover it anyway. So PWD means print working directory, okay? This tells you where you are in the file system, okay? Print working directory. It tells you where you are in the file system. So the slash here at the left side is called the root directory. So that's the top of the file system. And then each directory is separated by another slash, okay? So we are sitting in slash NVMe, slash H, which I guess stands for home, slash your username, and then slash this EuroCC training, which we just created and CD'd into, okay? So that's where we're sitting now. Okay, some good to know aliases. Dot is an alias for the current directory. Just a single dot is an alias for the current directory. 2 dots is an alias for the previous directory, just one up. Okay, and this tilde is an alias for your home directory. Okay, so let me give you an example. So if I go cd dot dot like this, or just dot dot, then I will go one up and I will be back into my home directory. That's why when you're in your home directory, you see this tilde, because as I said, tilde is an alias for your home directory. Okay, if I go back to EuroCC training, and if I try to go 2 directories up, okay, well, actually, let me PWD this again. So if I go 2 directories up, I should end up, indeed, I end up in H, right? And so here now are everybody's home directories, okay? I might not be able to access all of these. Actually, I should only be able to access my own. And CD with no arguments just takes you back to, you just go home. You just go home, okay? CD with no arguments just takes you home. Okay. So if I type PWD here, then you see I'm back at my home directory. Okay. So I want to go now back into this EuroCC training. And under here, I want to make a directory 01, which will be this first exercise we will be doing after the break. So mkdir 01, and then cd into that one. And pwd, again, just to practice and confirm that we are indeed under our home directory, under EuroCC, which is under our home directory, under 01, which is under the EuroCC. Okay, so we already created a kind of a hierarchy there. Okay, now what I want you to do is copy a program from the shared space here, NVMe scratch edu19. There is a 01, so I already put these files there, okay, so they should be there for you. What I want you to do though is copy from the shared space to your home directory this program, which I call prog-01.c. So if you have the slides in the browser, feel free to just copy paste this. But let me just explain what this means. So this is the copy command. It means copy, right? CP, copy. And it takes 2 arguments, the file that you want to copy and where you want to copy it to. And remember what I said, dot is an alias for here. So you're saying copy the directory to the directory that I'm currently in, is what this says here. Okay, that worked. And if I list the current directory, I see the program there available. Okay. So if we can all be at this point. So at some point, I will need you to edit files on the remote server. So you can use a text editor that is running there, or you can use VS Code if you know how to do that to edit the file. Who doesn't know how to edit a text file on the remote server? Who has never done this? Yes. Okay. Okay. So can I see the hands again? Sorry. Okay, that's fine, because that allows me to indoctrinate you into Emacs. No, but no, but so if you know how to do it, it's fine. If you don't, you just follow along what I do, and I will be using a terminal text editor to do this. So you can just follow what I do, right? And and I'll be and I'll be explaining sort of the steps to do this. Okay. But for now, so if you know how to do this, as I said, do what you want to do. If you don't, then follow my lead. So I will be using Emacs. So I don't want to edit this file. I just want to look at it, but I'll use Emacs anyway. So type Emacs, E-M-A-C-S. You may or may not need that option. Just keep it if you just keep it for the meantime. And then the name of the file, and then Emacs opens up, and you see the program that we're going to compile and run after the break, right? You see it there in the terminal. Okay. Before we go for the break, I just want to make sure that you know how to leave and go back to the terminal. For Emacs, for the case you're using Emacs, you just hold down Control with one finger, and then you type X and release X, and C and release C, and then you're out. Okay, I'll do it again. Hold down Control, and you tap X once and release it, and tap C once and release it, and then you're out. Okay? Okay, so I'll stop here, and then we go for a break. Okay, so I think it's time to move on, so that we also have some time for the next part. So where we went for a break, I was explaining this first program that we're going to look at. The program is not that important, to be honest. This is just an example to show you a bit how to compile some code on the cluster and then run it using srun. So far, what we have done is we've used srun to run this Linux command, which is called hostname, which prints the hostname. But here I put an example that we can actually compile ourselves. Compile ourselves on the cluster, just to explain a bit this concept of the module system. So, but in any case, just so that I don't just throw this program at you and you don't know what it does, I'll just briefly try to explain. So this is a C program. If you're not familiar with C, if you're not that familiar with C, don't worry too much about it. The important bit is this is a variable declaration for the variable hostname, right? It's a string hostname, right? This is an integer declaration for a variable P. And then in these two lines, we basically fill up the variables H name and P. We call a system command called getHostname, which puts the hostname of whichever node or server is running this program into the variable H name. And then we call getPID, which gives you the unique Linux process ID of the process that is running. Okay, so in Linux, this is just the way. I mean, it's not exclusive to Linux, but Linux, when you boot it, the first process is process 0, I think init-d or something, and then each new process that runs gets an integer number as a process ID, right? So if you're ever on a Linux system like I am now and type ps, then you can see that the shell that I'm running which is bash, has this process ID, right? And the command ps that I actually run is the only other running process which has this process ID. It's a long integer which represents the ID of the process there. If I type ps again, then bash will have the same process ID, but this ps now has a new process ID because this is a new ps process run. Anyway, don't worry about it too much. It's just the unique integer that is the process integer. So what we're doing here is we're getting two things: the host name, as I said, and the process ID of this process that is running. And then we print it to the screen. So this is all this program is doing. Okay, it's a very simple program.
But as I said, what I want to show here is how to use this concept of a module system, which is available on this cluster. Okay, so we want to compile the C file now into an executable. If you're familiar with Python, for example, or another interpreted language, this is not what you usually do, right? So if you're familiar with an interpreted language, you have a script, and then which is called, I don't know, something.py, and then you run Python, and then the script, and then the Python executable passes the script. Okay, C is a compiled language, it's not an interpreted language, which means we have a source code file, this file here, which we want to compile into an executable and then run it. So that means we need to invoke the C compiler in order to run it, in order to compile it and then run it. Okay, it's very common in HPC systems, as is the case for this system, to have multiple versions of compilers and other software installed, right? So there's GCC compiler version 14, and then a new one comes out, and you don't want to immediately change the whole system to be, I don't know, GCC compiler version 15, and then everybody's code breaks, et cetera, et cetera. So what administrators usually do on these shared systems is that there is a so-called module system. Okay, there's basically multiple versions of the compiler installed at different, at specified places on the system. And then you as a user select the environment that you want to use, which will have the C compiler, which is version 14, and an MPI compiler, which is version, I don't know, 3, and et cetera, et cetera. So you sort of pick which version of each software that you want to use. So this can be done in various ways, but the specific ways that is being done on this system and on most HPC systems is with the so-called module system. Okay, so you use the command module, right? There's a command that's available to you on the cluster module, and then you add as an argument a specific I don't know what the terminology is. So it's module and then I guess a subcommand like available. Module available will give you all the modules that are available on the system. It's a long list. You don't need to go through it, but you can just see all the various versions of all the different libraries that are available on the system. Okay. So the same is so what we want to do now, if you're on a fresh system, if you're on a freshly logged into the system, so if you type module list, you should get nothing. So no module is currently loaded in my environment. Okay, so none of these modules that I could load here is actually loaded now, right? Which means that if I try to do things that you normally would expect to do in a command line like I don't know, compile, etc., what you will get is either no compiler or you will get the default compiler, which might be very outdated or So before we go on to compile this program here, this program prog01.c, before we go on to compile it, we want to make sure that we have the right modules loaded for this. Okay, so let me move on to this. So we will be using the GOMPI module. Okay, it's not important exactly which one we use here because we won't be using MPI, but I tested this with GOMPI or GOMPI. I sometimes call it. I don't know if everybody else calls that. But this is the GNU C compiler coupled to the open MPI implementation of MPI. Not relevant here, which version of MPI we're using, but this is how this was tested, so that's why I use it here. Okay, so if you want information about this module, you can do module show comp. This gives you some information about the description about what this module is about. And then if you want to load it, module load comp, okay. And now if I do module list, I see the modules that are loaded. So really, what I should have said before is that this GeoMPI is really an alias for a collection of modules, which are these 17 modules that were loaded when I said module load GeoMPI, okay? So I typed module load GeoMPI, and somebody, probably mean us, decided that GeoMPI means these 17 modules, okay? Which is fine, because this is what, well, one is actually GeoMPI. So basically these 16 modules, I should say, right? So this GCC library, this zlib library, this NUMA control library, this libxml library, this hardware, right? These versions of these libraries. Okay. So once we have that loaded, now we can compile our program. So I'm going to compile it here. Maybe move that up so you can all see it. So GCC -o P01 prog01. Let's see. Okay, so that's the compiler that I want to use, GCC. That's the program that I want to compile, and -o P01 just says, when you compile this, name the executable P01. That's what that means. So now I see that I don't only have this prog01, but I also have the executable P01. Okay, if you don't specify an executable with -o, then you just get the default output, which is a.out. Okay, but my examples assume that you used -o P01, and so I will assume that the executable that you have is named P01. Okay, so this P01, as I said, is now the executable version of the code that I had in this slide here. And so when I run it, let's see what it should do again. I covered this, but let's see again. So when I run it, it should basically, I should see this when I run it, which is, it should say hostname, colon, and then the hostname, and then a comma, and then the word PID, and then an integer, which is the process ID. Is that what I get? Let's see, P01. Yes, so when I run it, I get hostname, run 02, that's correct. This is indeed the hostname that I'm running on. And the process ID is indeed, you know, a long integer as I expected. Okay, so what have we done? We've selected a module, a version of the C compiler that we want to use to compile this program. We compile the program and we run it on the front end, right? But this is not necessarily what we want to do. Yes, okay. I told you not to run programs on the front end, but this is a tiny program. It's not really going to stop anybody from doing anything. You shouldn't run long jobs on the front end, yes. But thank you. Thank you for putting me in my place. Thank you. More of that, please. So, okay, so let me just see what I want you to do next. Right. This we covered. Yep. Okay. Yeah, so if you run it on the front end, you get, you know, process ID and a host name. So now let's try running this on some nodes. So you just follow the same approach that we did before. You use srun. You specify how many nodes you want, how many processes you want to use, which partition you want to use, the reservation, blah, blah, blah. And then at the end, you put the name of your program that you just compiled, right? So let me just copy that. And if I do that, then, is it going to sleep? Is it asleep again? You're really aggressive in putting these nodes to sleep, huh? Okay. It's just I just decided that I want to use 4 processes, 2 on one node, and 4 processes on 2 nodes, which is fine. I mean, there's no real reason why I selected 4 here instead of anything else. Yes, but what I want you to see is that each one is a different process, right? How do I know it's a different process? Because each one gets a unique process ID. Okay, so this one, when I was writing the slides, so 2 days ago, let's say, when I run this, one of the 4 processes run on the node with hostname GPU02, and the process ID was, I won't read it out, that one. And then 3 of the 4 processes run on the other node, which was GPU03, and each one got a unique process ID. So these processes were running in parallel, okay? Yes, 2 each. Yes. Yes, so I don't know what it is. So I'm going to cancel this, but hopefully the node will still wake up. So I don't know this at the top of my head. So what I'm going to do is look at the manual of srun. Can I do this? No manual. Oh. So srun, maybe I should do this. So I'm going to look at the help screen of srun and see what the option is for specifying 2 processes per node. So I could scroll through this like this, or I could maybe, here it is, n tasks per node. That's probably what I want. Okay, so now I can come back to here, and I can say n tasks per node equals 2, I guess is what I want in this case. But then probably I still have to wait because the node is still booting. And then hopefully, if it respects this, I should get 2 on one node and 2 on the other. Yes. Okay, so there it is. So that indeed worked. So here's the thing. If I do something like this, then it says that basically the way that I asked for this is not possible. Okay, good. But if I do remove minus n5, then this will work and will do exactly what I did before, because now I'm saying I want 2 nodes, 2 tasks per node. So it's obvious that I want 4. If I were to put minus n, it would have to be 4, right? So I guess, yes, I mean, here, okay, here it did something else. It says, can't honor n task per node set 2, which doesn't match the request. Okay. So Slurm has been implemented to deal with the situations where you conflict with yourself, and sometimes it will sort of help you by not honoring this. Other times it will say, I won't do it at all, and then, okay. So you decide which way you want to specify, I guess, is the answer. Okay. Questions? Up to this point? No, good, okay. Right, so the processes that are run on the same node and on the different nodes are run in parallel, okay? That's the key point there. Okay, step 2. So now I'm going to show you a different example, which is a way, which is sort of my approach to show you a bit how you can run something in parallel, run a task how to parallelize sort of a task, but in the sort of simplest way we could do without actually going into the code and implementing the parallelism in the code. Okay, so what we will do here in this second exercise is, yes. Okay. Yes. So we haven't seen batch jobs yet. So what we have been doing so far is interactive, but I'll cover this bit. Okay. So so what I will do now in the second exercise is not really what we do in HPC in general. Okay. So what I'm going to show you is how to run a specific example that we want to do in parallel without actually going and implementing parallelism inside the code. But usually what you want to do, right? Can I help you, sir? Well, if I find it, I'll be sure not to tell you that. So we will be running a program that we want to run, a task, I should say, not a program. We will be carrying out a task, speeding up a task by parallelizing it, by using more than one processes. But the way we're going to do this is sort of without actually going inside the code and implementing the parallelism inside the code. Okay? What you eventually want to do if you are interested in running on an HPC system is implementing parallelism inside your code, right? There's various ways to do this. You can do this with MPI. I'm just throwing out like sort of ways that one can do the sort of message passing using MPI, or multi-threading, for example, using OpenMP. Or if you want to parallelize across GPU threads, you use GPU programming or CUDA, which we will see afterwards, right? So those are the sort of the common ways that one implements parallelism in their codes. And that's probably what you're more interested in doing. But first, I want to sort of introduce you to this by showing sort of a very simple way one can implement parallelism without actually going into the code and implementing the parallelism in the code, okay? Just by manipulating the Slurm script, or the, using Slurm. Okay, so first we will make a new directory under this EuroCC training directory that we created, just to separate things a bit. So I'm going to cd one up, and I'm going to make a directory here, 02. I'm going to cd into 02. Okay, so that's where I should be. And now I'm going to copy this program that is called Fletcher32.c. from this shared space. Like this. Okay. So what this program does, well, maybe I should, yes. So now we're going to inspect this C file that I asked you to copy. Okay, is everybody... I don't want to leave anybody behind. So please, if I go too fast, just point that out to me. Okay, so this is the main program. Again, there are some comments there which you can take a look at. I'll leave you some time to do this, but can you still read it if I make it a bit smaller, just to fit more in the screen? Okay. Rather than going through the lines and explaining what each one of these is, because you might not be that familiar with C, what I'm doing here is I'm taking a file that I provide to this program. So this program takes as input the name of a file. And what it does is it goes over the bytes of the file, right? Just byte by byte over the file, and computes what we call, it computes a checksum, right? A hash, you can think of it. So it computes a checksum. The specific checksum it computes is the 32-bit Fletcher checksum of this file, okay? So it basically takes, you know, however big the file is, you can always run this kind of checksum on it. It just basically digests the file, however long it is, into a hexadecimal number, which is the checksum for that file. Okay, this is not the best checksum available on the market, but it's a simple one. So I just don't worry about it too much. It's not important that this is sort of a safe checksum or anything. It's just the process that we do on a file to get a short output that represents that file. So this is what this program does. And so I will compile it like I explain here on the slide, right? GCC, the name of the file, -o, and I'm just going to call the executable F32. So I'm compiling this C code now into an executable, like I did before with this simple hostname. Okay, there it is. And this program now needs an argument. So when I run it like this, it says, the way you're supposed to use this program is the program name, and then a file name is an argument, right? It needs the name of the file that it will compute this checksum over. Okay, so I have prepared for you 10 files that are big-ish, right? They're not too big, not too small, but they're big-ish. So you can list them here. You can list them, right? They're on this shared space, 10 files. And so these are, these are files that I would like to compute the checksum over. So let me see. Let's try one of these. Which one do you want? 03.txt. Oops, what did I do there? 03.txt. Okay. It runs. So this I shouldn't do. Indeed, I'm running this on the front end, but Minas will let me do this, right? I'm allowed for today. So I'm running this on the front end, and this is the hash. This is the checksum of this file. If I run it again, it should give me the same checksum, right? It's reproducible, but each file should have a different checksum. Okay, so I'll leave you a few minutes to just sync up to this point before I go. Let's see. Okay. Should I stop for a bit longer or everybody's synced up? Okay, I'll go on. Any questions about any details or even not? No? Okay. So, okay, so so there are 10 files there that I want to compute this checksum on. And I mean, let's just try one of these. So I put this command time in front. It just tells me how much time the command that I'm going to run takes. This will take about 1 to 2 seconds. Yes, it says that this takes 1.8 seconds, basically in real time. So 2 seconds. So if I want to, there are 10 files there. So if I want to compute the checksum, it'll take about 20 seconds. Okay, this is not the hardest thing to do, of course, but it's just to demonstrate a bit, right? So if I can run this in parallel, so if I can run this over 10 processes in parallel, then computing the 10 checksums should take me about 2 seconds. Whereas if I only have one process to go over them in a loop, then it'll take me about 20 seconds. Okay? So what I want to show you is how to use a script to run these 10 checksums in parallel using srun and sbatch and the things that we learned or will learn, so that this runs in parallel on the cluster. Okay? Okay. So yes. So the compute nodes have 40 cores each, so it should be okay to run 10 in parallel. Okay, so first we will start by using a batch script rather than what we've been doing so far, which is running interactively, okay? So interactively means that so far we have been like, let's say running in real time, right? So we have been typing srun and then the commands, and then we type enter. The job goes onto the node, and then sort of we interactively see, in real time, we see the output come back to us. But imagine if you want to run something that takes longer, like a few hours, right? You don't want to be there stuck on your screen and leave the computer open or whatever for those several hours for the job to run, because you might want to power down your laptop, go somewhere else, right? The terminal will disconnect. You will lose the session. So that's what using this non-interactive or using a batch script does, okay? It allows you to sort of run these jobs in the background, okay? So for that purpose, we will use a batch script, and I already have a batch script made for you. It's under NVMe scratched edu1902, and it's called fletcher.sh, okay? And I will copy it here, but then I'll copy it here, right? So there it is, fletcher.sh. And then I will go through it a bit so that we understand what's going on. So maybe I start from the end. I start from here. So that should be familiar to you. At the end of the script, what we're going to do is srun the command that we've compiled, F32, and then the file we want to run, the Fletcher checksum on. So for now, I'm just going to do one file, okay? Just to demonstrate it. Later, we will add the 10 files that we want to do in parallel. For now, we just do this single one, f that is 03.txt. Now, let me explain a bit these other options. So a lot of these options are the same options that you would otherwise put to srun, right? But now you're putting them there in the header of the file, which has these sbatch keywords, okay? So whatever you can add as an option to srun, you can also add up there, and then it's implicitly inherited in this srun command. So it would be as if you run this srun and then added these options between srun and the executable, okay? That's what we're doing here. So we're putting the options there at the top, and then we're adding srun without any options because srun will inherit the options from above. So some options that are new to us here. So this option should be not new to you. This option should not be new to you. This shouldn't be new to you. This one is new. This is the time. So this just says, if it takes more than 2 minutes, then stop the job, right? That's what this T means. It means allow for this job at most 2 minutes, okay? This is not new. This is not new. This we recently figured out how to use, right? Task for node. Excuse me. Okay, so these three are new. The first one, it just gives this job a name. It's just the name that you can use to identify this job when you look at it in the queue, for example. We'll say more about this later. Okay, now, the thing is, as I said, the purpose of this script is to run it non-interactively. So you will send this script to the background, and this will run in 2 minutes, but imagine if it were longer and it took, hours. At some point, you just go away. And the question is, okay, but where does the output that I would see on the screen, where does that go? Well, now it's not coming to the screen anymore. It goes to files. And these are the two files where that output that would otherwise go to your screen goes when you run it interactively. So there's a text, there's the file where the regular output is sent, -O. And then this is the file where the errors are sent, if there are any errors, okay? Hopefully when we finish, this one will be empty because we don't want to see errors, okay. No, and the other thing that I put here is I wrapped this command around two date commands. So date just gives you the current date, right? So it tells you actually the time and the date. And the reason I did this is I want to see basically how long srun took. And to see how long srun took, I'm going to print a timestamp before and after the program runs, okay? And this specific format that I chose actually shows me milliseconds rather than seconds, so that I can have a bit more accuracy on the time that it takes. So we can now just go on and submit this job. So sbatch fletcher.sh will submit the job. Let's see, sbatch fletcher.sh. Okay. And it says submitted batch job, and it gives me a number. I can check the status with SQ, and if I use this pattern -u $user, then I see only my jobs, and it's already run, so I don't see anything. Let me just run it quickly again, and then do SQ so that you can, oops. Okay, so here's, now I typed SQ, and I've actually managed to do it fast enough so that I see my job in the queue. So the status here is R, means that it's running. You may see PD if it's pending, or you may see CG if it's completing. These are the nodes that I've been allocated to run on. This is GPU 03 is what it's running on. And this is the time that it's been running. And this name here is just what I, excuse me. The name here is just what I specified here at the -j option, okay? Okay, and now I typed it again, and this job is over, so I get nothing, okay? Right. So, what is the output of this script? Let me open it again so that I can oops, not that one. Again, what I expect to see is the output of running this checksum on this file 3.txt, 03.txt. And I want to see 3 lines, basically. I should see 3 lines, date, that output, and then date again. So a time, the output, and then a time. And I can indeed see that there are these files created, right, from running the job. And if I look at the output, then I see the current time, the time at which it run. So that was about 2 minutes ago, right? With milliseconds accuracy, the output of this F32 file, and then the time when it finished. So as you can see, indeed, it took about 1.4 seconds to run, about as long as it took when I run it on the front end, okay? Yeah. Okay. Okay, so we haven't done much, right? We've just, but we at least have a script that now we can start modifying in order to do 10 of these files in parallel. But first, let's do the 10 of these files sequentially. So I could just go ahead and do something. I mean, so one way to do it, don't do this, but one way to do it is just do this 10 times, 1 for each file, right? So I could go and into 0, 1, 2, right? I could do this, but we're smarter than that, right? So we want to use an iteration to do this. And okay, so let's do the iteration, right? So I have this in the script. I don't want to turn this into a bash tutorial. There's plenty of resources that I can point you to if you want to learn bash, but probably you can read this and understand that this is a loop where I goes from 0 to 9, right? So now there's a variable I inside this loop that takes the value 0 to 9. And somehow I want to turn this I into the file name so that I add a txt to it. And the way I do this is by declaring a new variable. And the only reason I need a printf here is because I want to put this 0 at the beginning, right? I want it to be formatted 0, 0, 0, 1, 0, 2. And this is my So I could put $0 but then it wouldn't work if I had a file which is called 11.txt, right? So the way this means take two spaces, put a 0 in front, and put nothing at the end of the decimal. I mean, okay, just believe me that this is this is the right way to do this. But then I can put file name there. Oh, and I already put the txt here. So that should be sufficient. Okay, so now we've changed our script so that it does the 10 files one after the other. So it took about 1.5, 2 seconds to do one file. So let's submit this and see if it indeed takes about 20 seconds. Okay, so it's running. It seems to be taking longer than the other one, right? It's going. Okay. So now if I look at f32.txt, oops, f32.txt, then I see the date. Right, because before the for loop, I have one invocation of date. So I see the date, the timestamp. I see the 10 checksums, and then I see a timestamp again. And indeed, if I take the difference between that and that, that's about 15 seconds. Okay, so it agrees with more or less what I expected, 1.5 to 2 seconds per checksum times 10. Okay. And now I want to run this in parallel because I know I have more than one process that I can run in parallel on these nodes. So far, I've just been running one process. Okay, so how to do that? Okay, that's just what I would. Okay, so now let's run this in parallel. So how to do that? So we start off from the script that we have. Okay, but obviously we need to modify it. So the first problem here is that we're only running on one process, one node. So let's say I want to run on 2 nodes, 10 processes with 5 tasks per node. Okay, right. So this all means that I want to reserve 5 processes on one node and 5 processes on the other node. But what did I say? I said that, okay, but the thing is that if it comes down here now, then this srun will just inherit these options, right? And put them in srun. So that's not really what I want to do. What I want to do is I have this pool of 10 processes, but each iteration I want to go to a different process, right? I want to distribute this. So what I want to say here is minus -1, right? I want to say, you might see 10 processes there, but this instant of srun in this iteration of the loop should only take up 1 process, okay? Right? Because it should be 1 per iteration. Okay, that's one thing. The other thing is I need to add -- exclusive, which means that this instance of srun needs to run exclusively on one of those 10 allocated processes, so that another process doesn't go on the same process. So I need to specify this -- exclusive, and then right, and then okay, the -n1 here is a bit redundant, but if I want to be very explicit about what it's doing, I should put that there. Okay, but still, so far I've not really done anything, because the way Bash works, this is not a problem of srun, but the way that the shell script works is that it will wait for this line to finish before it goes to the next iteration. So this is not a Slurm thing that I'm going to show you now, but this is a sort of a Linux shell sort of feature. If I put an ampersand at the end, that makes all the difference. So what this is doing is, in each iteration, this line is being sent to the background so that it can run in the background, and then the iteration moves immediately to the next iteration. The loop, I should say, moves immediately to the next iteration. So send this line to the background and go immediately to the next iteration before this command completes, okay? So that's what's actually going to give us the parallels. Okay, if I keep it like this, there's a bit of a danger in that all the processes will be sent to the background. The script will come to the end and might actually, depending on how the system is set up, might actually finish the job before these processes are finished. So one thing you can do to ensure that this doesn't happen is to add this wait. Again, this is a Linux, this is a shell command, this wait. This is not a Slurm command, which just says, don't go on to the next line unless all the background processes up to this line have completed, okay? All right. And now this should be all we need to do here. Hopefully I didn't forget anything, but if I send this, then it should run for, yes, okay. So I see the 10 checksums like before. Nothing should have changed as far as that's concerned. But now it should be done in less than, yeah, it took 2 seconds, okay? Okay, so it took 2 seconds, whereas before it took 15 or 16 seconds. So I'm pretty confident that this was run in parallel. Another thing that you might notice is that these are now more or less out of order, right? So the order here is random because there is no predictability in which of these 10 processes finish first. It's just noise, it's just system noise that is influencing basically which one of these 10 will finish first. I mean, they're issued in a sequence. So, 00 was issued first, 01 was issued first, but there might be something that allows 01 to finish before 00. Or in this case, for example, what I can say is that 08 finished before 02. But for random reasons. I mean, if I run it again, you'll get a different order, right? It's just this is which one finishes first is random. What is guaranteed though is that all 10 are finished before this is printed. Why is this guaranteed? Because the wait command is before the date. Okay, so the wait means wait for these 10 processes to finish before you issue the last date command. Okay. Okay. So I let you try this for 5 minutes or so, and then we can summarize this part before we move on. Questions? Okay. Oops. Okay, so when you do batch, right, this is parsed. So when you type batch in the script name, then Slurm only parses the part that I've highlighted there, right? So that means give me 10 processes, give me 2 nodes, give me 5 processes per node, okay? Then you have all your stuff here, right, which runs on the front end. Everything here runs on the front end or on one of the nodes that's been allocated to you. I don't know exactly. But then you hit this srun, and now's where you want to use whatever, srun, right? So srun has available to it 10 processes, 2 nodes, 5 processes per node. So everything that you put here should conform to whatever you put up there. So if I put here 20, for example, it'll complain. It'll say, I don't have 20. But if I put less here, it's okay, because I've already allocated 10, okay? So this here overrides, in some sense, that, but that is what batch actually reserves for you when it gives you the job. In each line, yes, yes. Yeah. So, so exclusive means different things depending on where it appears, okay? So that's actually something that sort of contradicts what I said about srun inherits what's up there, because if you put exclusive up here, then you mean that you want to allocate the nodes exclusively. Means don't give me a node which is shared by a different user, because some systems might be set up so that multiple users could use the same node. So if you put exclusive after an batch, okay, then that means give me exclusively the node. This is not how we're using it here. Here we're using it in the srun. And here it means that, I mean, it's similar to what I said before, but this now applies to at the task level. So it means that this single process that I'm going to run now at that one line should not be put on a slot where another process is already running, right? So that means, because if I don't put this exclusive, then what it will try to do, so the first time I go, it'll put 00, the file name 00.txt on the first core, let's say, whichever one is assigned the first core. And then in the second iteration, if there's no exclusive there, it might try to put this second process on the same core, right? Because I haven't said that because I haven't specified explicitly that this task is going to be allocated exclusively one slot, whatever Slurm considers a slot in this case, which is the CPU core, okay? Okay, so here's the thing. Okay, and different systems are set up differently. Okay, so the reason I'm using 2 nodes here is to make a point out of this, of what you asked for. So, okay, some systems are set up so that this here, whatever is here, runs on the front end. Okay, so what does that mean? This runs on the front end, the loop runs on the front end, this is all run on the front end. But when you come here, then it's sent to the node because it sees an srun. Okay? Okay, so if we do what you suggest we do, so we don't put srun here and only keep this, then this will run on the front end if the system is set up this way. Okay? I think that in our case,
This doesn't run on the front end. This runs on the first node of the allocation. Maybe Minas can help me here. So where does this run, on the front end or on the first node of the allocation? Do you know? The script. I think it runs on the first node of the allocation, but it doesn't. Anyway, so it definitely doesn't run on all the nodes, okay? That's for sure. So if it runs on one node of the allocation, right, then it would be okay to not use srun, right? As long as you don't want to use more than one node. But if you want to use more than one node, then all of these will run on the same node, and the other node that you've allocated there with minus N2, minus big N2, will be idle. Okay? So you need to use srun in case you want to use more than one node. In this case, where the script actually runs on only one of the nodes of whichever allocation you've been given. Yeah. In this case, no. In general, yes, you might see a difference depending on what your program, what the bottlenecks of your program are. So the processes on the same node are using the same memory, right? So if you have a program which needs some specific amount of memory per process, then it could be that you cannot fit 10 on the same node and you need to do 5/5, right? Okay, that's one case where you might want to use two nodes instead of one, right? Because you don't have enough memory on one node. Another case might be that you have a program which communicates faster when it's on the same node, right? And it's slower when it's distributed across nodes because it needs to do communication. In that case, you might want to run 10 on one node because it's faster. It doesn't need to do communication outside of the node, rather than using 5 and 5 on two nodes because the communication slows you down. So it depends on the problem. In this case, it's really not an issue if you use 5/2 or 1/10. You had a question. I'm saying actually something worse. I'm saying that it might decide to run on the same CPU core, two of these. It will try to run them in parallel, but on the same core, because you can do that. I mean, you can issue instructions well, I mean, at some level it'll be serialized, but you won't get a 10x speed up. That's what I'm saying. Yeah. Yeah. It will oversubscribe the CPU cores if you don't use exclusive. Okay. All right. Yeah. Okay. So if there are multiple users on, if there's a user on a node, right, and that user is using half the processes, and you allocate a node for you, and you say you want to use. Yes, but that's what I'm saying. So if you want to allocate now, if you want to allocate for yourself a part of the node that a user is already on,
then Slurm will give you the two processes that are not of the other, the processes that are not of the other user. So there's no danger there in being allocated cores that another user is running. So that's not, you won't need to use exclusive in that case. Okay. The thing is, now you have these cores for you, and you want to make sure that your processes are not stepping on top of each other. Then you use the exclusive. Okay. So if you use Assoc and you ask, for example, you ask for 2 nodes, then you're dropped into one of those nodes. Okay, how do you get to the other node? You need to use srun. Okay, so for the node that you're sitting on, you can use /f32 and it'll run on the node you're sitting on. But if you want to run something in parallel that also uses the other node, then you would use srun. Yeah. Yeah, it would be as if you're running it from the front end. It's the same. Yeah. Okay. We can spend more time here if you want, or we can move on to GPUs. Yeah. No, I mean, okay. I mean, okay. So these nodes have 4 GPUs each. Okay. So, I mean, I'll answer your question. This is not an answer to your question, but just to put the context. So these nodes have 4 GPUs each. So a user in the way this is set up, you can allocate a GPU or not allocate a GPU. And if you allocate a GPU, you have the GPU. If you have the whole GPU. You don't allocate the GPU, you don't have the GPU. Okay, so that's clear. That's how this is set up. Now, on a system where the GPUs are shared, then I don't know of any way to actually split a GPU up at this level. Okay, so as far as I know, it's basically fair game. If you're allocated a GPU with some other user, then if that user uses it all, then you don't get any of it. And if that user uses half of it, then you get half of it. But I don't know of any way you can actually manage this. At least in my experience, I haven't seen a system where this is managed. Maybe you can, but yeah. From the Slurm scheduler, I don't know if you can do that. I don't know. I don't know how you can. I don't know if, like, I mean, a GPU is more or less, you can think of it as a PCI device, right? It's not running its own operating system. So I don't know if it's that easy to say that, user number 1 gets to run on half the memory of this GPU, right? This is the problem. Yeah. I don't know if there's a real mechanism to do that. Maybe there is, but I haven't seen this, at least. On most systems that I've been using, you can either use a GPU or not use a GPU, but you don't really share a GPU. At least that's my experience.
There are 3 GPU.
4 on each node. 2 CPUs with 20 cores each. 20 each. So, yeah. So 20 cores each. They are, I think, hyper-threaded. So you really see 80 processes. Oh, yeah. Okay. Did we move on or? Okay. Just want to ask Stefano, what's the schedule exactly? I think we just go till the end, right? Or, but maybe, does anybody want a 5-minute break? Or if you don't, we can just keep going. Yes, keep going. Let's power through. Okay. Okay. So, well, I think yes. Okay. So before we do this, before we move on, I should just. Yeah, but yeah, okay. We might take a bit longer than 1:30. Is that okay? No. Okay. I'll try and do my best to finish on time. But I really need to stress this, okay? So what we've covered here is how to use the job scheduler, right? So I hope you're comfortable now and understanding what it means to reserve a node, to run on a node, etc. Interactive versus batch jobs, right? I think we clearly distinguish that. How to use the module systems to select an environment, and some basic things on how to run programs on multiple cores by using this Slurm script, right? So if you have some job that you run on many files, for example, right? Then now hopefully you know how to adapt this to your use case. Okay. So what we have not done here, but is very important, but it's very fundamental in HPC, is, so what we've done is we've parallelized the execution of codes that were otherwise scalars. So this Fletcher 32 program that you copied from scratch and you compiled doesn't know anything about multi-threading or parallelism or anything, right? So we sort of shoehorned the parallelism via running it in parallel with Slurm. But what we really do in HPC, and we will have follow-up training courses to do this, is you want to implement the parallelism inside your code, right? You want a parallelism-aware program. So you want to use multi-threading, for example, using OpenMP. Or you want to use distributed memory parallelism using the message passing interface, or MPI. So these are ways that you implement parallelism, and it's much more powerful when you do that inside your codes, okay? So I just want to emphasize this to say that this is the first step, right? So if this is the first time you're using a system which has parallel capabilities, then what we did today is a good first step. But what you really want to do, okay, is to program in the C code or whatever code, Python code, the parallelism, okay? All right. So ways to do that are the ways that I have here. But one other way to implement parallelism in your code is when you're using a GPU, which has by design some features which help parallelism, is to actually use it in a GPU. Okay? So this sort of segues me into my introduction on parallel processing on the GPU. Okay, GPU programming introduction. All right. So first I have some slides just to explain a bit the GPU architecture, right? Hopefully in simple terms, and some details about the specific GPUs we will be using for this example. And then we go to a practical, which is a short example, hopefully a short example, which shows how to get a very simple program running on a GPU, okay? So what I won't cover is some important features of the GPU, which are shared memory and thread schedule. So this, we wouldn't really have enough time for me to get into. But I will cover these basic things, which I guess are needed in order for any first GPU program. Okay. Okay, so this is a not to scale diagram on the left of a CPU and its memory, and on the right of a GPU. Okay, now the reason I've drawn it this way is just to contrast a bit, like the CPU with the GPU and some of the main features, right? So when you talk about devices in this way, there are some things there are some high-level features that you want to know, right? So some of these are obvious. Okay, CPU. The CPUs that we would use have 20 cores. Okay. The 20 cores inside the single CPU, they share a cache. This is this cache here, this orange cache. And then there's the memory, which is what you understand, very clearly as memory of the node. Okay, so that there is and by the way, on the nodes that we're using, there's 2 of these CPUs, right? I'm just showing one here. Okay, then there's a GPU on this side, which also has some processors, right? But really a GPU has many, let's say, lightweight processors, so they can't do everything, right, that a CPU can do. But what they can do is floating point operations, and but they do them slower than a CPU, but because they're more, they can do a lot of floating point operations in parallel, okay? They also share a kind of cache, right, here, and they also have a memory, which is a GPU memory. Now, okay, so the GPU cores can access the GPU memory faster. Look at this number here, 900 gigabytes per second. That says gigabytes per second, sorry. Okay, so the GPU cores can access GPU memory faster than a CPU core can access CPU memory. Okay, so that's one way the GPU is faster. The other way the GPU is faster is what I mentioned before, is that there are many cores, they're slower, but they're much more than the CPU cores, and they can do floating point operations, okay? But the the catch is that you always start up from the CPU, so that means that your data is going to start off sitting here, okay? So in order for the GPU to use the data that is sitting here, you need to move them over to the GPU memory over this relatively slow connection, which in this case is just the number for PCI Express, which is 32 gigabytes per second. So I think that number is for PCI Express 3, PCI Express 4 is a bit faster. But in any case, this number here will always be slower than this, okay? So that means that, yes, you can process the data faster using the GPU cores because the memory bandwidth to GPU memory is faster. But first, you need to eat the cost, let's say, of moving the data from CPU memory to GPU memory, okay? So that's sort of the high-level pluses and minuses to using a GPU, okay? If you have the data on the GPU, then most likely you can process it faster. But the problem is you have to process them fast enough so that it pays off to actually wait for the data to be put on the GPU. Okay. So this is some numbers. The numbers that I have there reflect the bandwidths and the performance of what we have on what we will be using for this exercise. So one thing to keep in mind is that the memory bandwidth of the GPU, so the speed at which you can read and write data here, is about 900 gigabytes per second. These are V100 GPUs. These are two generations. This is like, there are two generations of GPUs since these GPUs were released, okay? And the current versions, for the current versions, this number is of the order of 2 to 3 terabytes per second, just so that you have an idea of where we are. Okay. So I just want you to keep in mind this number, because this is something that we will be referring to in order to see if the program that we run runs as fast as we expect it to. Okay. Now, the way that we use GPUs, and this is true not only for NVIDIA GPUs that we will use here, but basically for also AMD GPUs, etc., is you use this offload model. Okay, there are other ways to use GPUs, but those are not so, let's say, common. And most of the times, really what you're doing is using this offload model is just hidden, right, by, you know, syntactic sugar, etc. But basically, what happens in any program that is going to use the GPU is that first the program starts on the CPU. So the CPU loads the program, and the main program, for example, in C, is executed by the CPU. The CPU runs a program. It has some data in main memory that it wants to process. It ended up in main memory either because you read a file or you generated the data, right, by running some program. But anyway, there's some data in main memory here, and now you want to use the GPU. So what you need to do is the CPU has to explicitly move this data to the GPU via a library call, okay? So you move the data from the CPU to the GPU memory, and then the CPU dispatches GPU kernels. Kernels are just little functions that run on the GPU. So once the data is on the GPU memory, now you offload kernels to the GPU. That's why it's called an offload model. So the GPU runs whatever it does, that reads the GPU memory. The GPU does not have access to this memory. The GPU only has access to that memory. So first you need to copy the data there, then you process the data. And now when the program is done, you copy the data back from the GPU memory to your CPU. And now you can do something like print it to the screen, put it in a file, you know, whatever you want to do with that data once it's back on. But the key point here is the GPU is not running an operating system, right? It's not, I mean, it runs something which is like an operating system, but you don't have a shell where you're inside the GPU like we did with the nodes, right? The GPU is a device. You run your programs, they start on the CPU, and then they send things to the GPU. This is the paradigm you have to keep in mind when you're programming for GPUs. Okay, now, I can probably go through this quickly. Okay, so so I should probably go quickly through this because we're not going to use much of this. But the let me see. Yes, okay. So the GPU, the way you should think of the data that is available to the GPU is that there is the so-called, so what I drew here as GPU memory, now I'm zooming in to the GPU, okay? And so these are the CPU thread, the GPU threads here. So there's many of these processes that you can run on the GPU, and they can have two kinds of memory that they can look at. They can look at this global memory, which is just this memory here that I drew before. but they also have faster memory that is very close to them. Like, you know, like variables, like if you have in the GPU, you say like float X, that X will live in this local memory that the GPU can access very quickly. So the model is that the GPU can access this global memory with this speed of 900 gigabytes per second, but then it can access their local memory here much faster, like an order of 2 orders of magnitude faster. The other thing to keep in mind is that threads are, there's like a hierarchy of how you split up the GPU threads how you use the GPU threads. So there is a concept of a block, okay, which is just the name of a group of threads. And then what you can do is you can run a kernel using some number of blocks, okay? So you as the programmer can say, I want to have 8 threads per block, and I want to run this kernel using 16 blocks, okay? That means that basically you will be running your code on 16 times 8 threads, but the grouping is 8 threads at a time, times 16 blocks, okay? There is a reason for this kind of subdivision, which I will get into, but basically there's 2 things. The threads within a block can share memory, but threads across blocks cannot share memory. So that's the main point, right? And the other thing is that there is a maximum number of threads that you can use within a block, but there's effectively no limit on the number of blocks that you can use, okay? So you can have millions of blocks, but you can only have up to 1,024 threads per block. So this number, 1,024, depends on the architecture, but in any basically GPU that you will run on, it's really 1,024. It hasn't changed for many years. It's this limit is 1,024. Yes. Okay, I think that's all I want to say here. Okay, so these the GPUs we will be using are NVIDIA GPUs, so I have to use some NVIDIA terminology, but the same things that we will do here are applicable to also other kinds of GPUs like AMD. It's just that some of the terminology and the names are different, but the concepts are the same. Okay. So to program GPUs, we use CUDA, which is an acronym for Compute Unified Device Architecture. It's basically C with some additional stuff that you use to run on GPUs. There is a compiler that is basically a wrapper to the C compiler, which is called NVCC, NVIDIA C compiler. And then there's a library with functions for using the GPU. Okay? Yeah. For NVIDIA GPUs, for CUDA. Yes. So I'm pretty yes, I think you can use the GPUs with other compilers. So other compilers have support for NVIDIA GPUs, right? So you don't necessarily need to use NVCC to compile that. But I'm pretty sure that you need to have anyway the CUDA, the NVIDIA SDK installed, because those compilers basically use CUDA libraries anyway to actually compile the code. So I'm not sure if there's a completely standalone separate compiler. I'm not too exactly sure about that you can use to compile a GPU codes. Okay, so I'll go through some commands, but we will see these in the example that follows. But the first thing that you want to do in any, well, first of all, I should say that some terminology. This is NVIDIA terminology, but I think it also applies to AMD GPUs. When you see host, you mean the CPU. And when you say device, you mean the GPU, okay? So this is important because a lot of the function names or a lot of variables, they say either host or device, and that's to distinguish between the CPU basically and the GPU, okay? So, so the first function that you will inevitably want to run is this CUDA malloc command, which just says, allocate some memory on the GPU and return to me a pointer to the GPU memory. So there's a CUDA malloc and there's a CUDA free, okay? Okay, then the second probably command that you want to use is a memcopy. So this means copy memory either from the CPU to the GPU or the other way around, copy memory from the GPU to the CPU. So you can either issue it like, so either direction is the same function, CUDA memcopy. The difference is that there's this flag here, there's this basically variable that either says CUDA memcopy host to device. Remember, host is the CPU, device is the GPU. So this means from CPU to GPU, or you can do the other way around, which is device to host. Now, the semantics of this function are a bit particular in that when you do it this direction, host to device, then the first argument should be a pointer to device memory, meaning it should be a pointer that you got from CUDA malloc, whereas this one should be a pointer to CPU memory, meaning it should be a pointer to memory you got from malloc, not CUDA malloc. But then if you go the other direction, you should switch them around, okay? Okay, and then there are, yes, of course. No, if you do a CUDA memcopy, that doesn't say anything about the data that's on the GPU. You just copied it. If you want to release it, then you need to explicitly free it. The GPU memory, well, I mean, it's good practice to free it before you exit the program, but you might want it to live on the GPU even after you free it, even after you copy it. So that depends on your application, but it's good practice to free it before you close the program, yeah. Okay, now, a function that you want to run on the GPU looks like any other function, more or less, that you would write to run on the CPU. It's just that you add this decorator to it, this attribute, which is underscore, underscore, global, underscore, underscore, okay? So this, if you put this in front of your function, this tells the CUDA compiler that this is a function that I would like to call on the GPU, okay? So far, what we've been doing looks exactly like C. There's no special stuff here. This underscore, underscore, global is also basically either ignored by C or, you know, is a special attribute to C. But now, this stuff is not standard C anymore, okay? So this is the special CUDA syntax. So if I were to hide this, what I highlighted there, that would look like a regular function call. But the fact that I put these greater than and less than signs is telling CUDA that I want to run this on the GPU, okay? And I'm specifying the number of blocks and the number of threads per block.
Okay, so I can specify the number of blocks and the number of threads per block at runtime. So this does not need to be specified at compile time. If I can leave this as being variables that are undetermined at compile time and just pass them on as runtime parameters. Okay, so I don't need to know this necessarily when I compile. But when it does come time to run this, I should specify the number of threads and the number of threads per block. You can also use a multi-dimensional number of threads, etc. Okay. Okay, now, inside the CUDA kernel now, so inside the CUDA kernel, I can pick up the thread ID and the block ID of the currently running thread, the currently running process that is running this kernel. Okay, so if I let me just use an example. Let's say just small numbers, just to make this point. So let's say I run this. I call this kernel like this, okay? And I use n threads. I put the number 3 there, just the number 3, and n block is the number 2, okay? This means in total 6 threads, okay? 3 threads per block, 2 blocks. In total, that means 6 threads, right? Not saying anything particularly complicated. So that means that this function will be run by 6 threads in parallel, okay? Inside the function now, I want to have a variable that distinguishes between these 6 threads, okay? And to do that, what I can know is the thread index, okay? The thread index is a number from 0 to 2. It's 0, 1, or 2, okay? It's the thread index inside. I should write this down. Don't know. Okay, so I specified n block to be 2. Is that what I said? 2 or 3? Yes. And n thr to be 3. Okay, so what that means is that this is a block. I have 2 of them. And I have 3 threads per block. Yeah? Okay. So there is a variable called thread idx.x. And that variable will be 0 for this, for the thread that's running the kernel, right? This variable will be 0, 1, 2. And for this one, it will again go 0, 1, 2, because this is the thread index inside the block. Okay? I also have another variable, which is this block idx.x, right? That one will be 0, 0, 0, 1, 1, 1. Okay? This is thread idx.x. This is block idx.x. Okay? Okay. Now, I want to make a unique number. Yeah. They're available to you. Yes, they're set by the runtime. Yeah. They have the correct values. Yes, exactly. Thanks. Yeah, that was important. So now I want, as a user, let's say I want to distinguish between, I'm not interested in the thread inside the block, but I am interested in a global thread index, right? So I want a number that's 0, 1, 2, 3, 4, 5, for example. I want to label them like this. Well, then it's, I mean, maybe you did this in some, computer science course or etc. So what you do is you basically make this calculation here. So this is the thread index plus the block index times the number of threads per block, which is blockdim.x, right? So this blockdim.x is just 3 because it's basically the same number as this, right? blocked in dim.x is just 3. So let's see if that calculation. So what I'm claiming is that the unique index will be this number plus this number times 3. So here it will be 0, here it will be 1, here it will be 2, and then there I need to do 0 plus 1 times 3. So I'll get a 3, here I'll do 4, and here I have 5, right? So that pattern there, that calculation will give you the unique index from 0 to 5, so that I can distinguish between individual threads rather than threads within a block. Okay, so that's a very common thing one does when you want to get the unique thread index. Okay, I'll just skip this because you can also do this multidimensionally, and then you have also a thread in the Y and a thread in the X and a thread in the Z. But okay, you can look at this later on. We won't need it for the example that we will do here. Okay, so in order to demonstrate some of these concepts, I've prepared an example, and this example does a specific operation, which is the so-called AX plus Y operation, okay? Where you have two vectors, X and Y, and what you want to do is scale X by a number and add it to the Y, to the other vector, and then output it as Y, okay? So the program that I will ask you to copy from here is currently using this on, is only implements this on the CPU, okay? Has no CUDA. But as a demonstration of how to sort of convert this, we can go step by step to port this simple application to the GPU using CUDA, okay? So for this, we will need to allocate memory on the GPU in order to hold X and Y, transfer memory from the CPU to the GPU in order to fill X and Y with the vectors that are on the CPU, call the kernel that does this operation, and to get the best performance, we need to talk about a bit about how the memory access pattern happens. Okay. So let me. Okay, so let's do this. You can follow along with me. So I'm going to make here 0.3, go into that, and then I'm going to copy this program here. Okay, and now this is the program. It's purely a C program. It uses OpenMP, but don't worry about that too much. It doesn't really matter. But this is what here's what it does. It allocates. So this is the X vector that I mean here on the slides. X and Y. But I'm allocating two of these. Okay, so I'm allocating two of these, and I'm setting them to the same values. Random values, doesn't matter what the values are, but I'm setting them to random values. And then what I've done is I have put two blocks in this code. One starts with a comment that starts with A, and the other starts with this comment that has a B in it. Okay, so there's two blocks in this code that do exactly the same thing. Okay. It's just that one operates on X zeros and Y zeros, and the other operates on X ones and Y ones. And the reason I've done is because I want just for the purposes of this exercise to demonstrate to you here, I want to keep this version untouched. And I want to move this part to the GPU so that I have a reference that is run on the CPU, which I can compare to. That's the only reason I do it.
in this weird way. Okay. So it does the same thing, and in the end, it compares basically y0 to y1. And if you get something which is machine precision, 10 to the minus 15 or so, then it means that the y0 and y1 were identical and the GPU did the correct thing. Okay, so I will compile this code, but before you compile it, you need to load the CUDA module, which has the NVIDIA compiler. If you don't load the CUDA module, the NVIDIA compiler will not be available to you. So, like this, okay, module load CUDA, it's also on this slide. And now I want to compile this program. And the important thing that I want to pick out from this compile command is that on this system, we have GPUs of different versions. So I need to take care here and actually give it the version of the GPU that I am going to compile for here, okay? So this is not something that you would know, like, unless somebody told you, but the specific V100 GPUs that we will use mean that I need to compile this for this SM7T architecture. Okay, I mean, there's no way you would know that, but all right. Okay, and I'm using OpenMP here. So I'm going to run this code on multiple threads for the CPU, right? Just to have a fair comparison with the GPU. So don't worry too much about what all this exports mean. This is just setting up the OpenMP environment, but then hopefully you can recognize this srun command, which is running the code on the CPU only now, right? One task. It's using several CPUs per task, that's okay. And as you can see here, I'm asking for one GPU, even though I won't really use that GPU. And it seems like, again, the node is gone to sleep. I only need one, so I don't know. Ah, okay, so some are already running it. That's good. Okay. I'm afraid we have to, maybe if I just do this, maybe it'll give me different mode. Oh, okay, so it's waking up the node. So again, this will take a few minutes. But in any case, what you see is it run the first block, which is AX plus Y, run on the CPU. And it gives you this. This is just the speed at which you read and write data for this process, which is should be, the peak is 130. So you get something close to 100, which is reasonable. Then it runs it again on the CPU the second time. It gets something again close to 100. And then it tells you the difference of these two operations, which should be identical. So it gives you exactly 0. Again, so what we want to do now is go step by step and move this bit so that it runs on the GPU, okay? So what we want to do is take the X vectors and the Y vectors, put them on the GPU, call a GPU kernel that will do this operation, and then copy the data back to the CPU, this Y vector now, which is the results to the CPU, so we can compare it to the other Y vector and see if the calculation was done correctly and we get a 0 or near 0 difference. Okay, so there's 7 steps to this. So some of these edits, so we need to add an include file. We need to write a kernel now that will run on the GPU, the function that will run on the GPU. And we will add this memory allocation function. So I won't wait for this. Okay, so here axpedo. Okay, so let's see. So first of all, include the CUDA runtime. So that's just adding an include file. Simple enough. So that just holds the definitions of the various CUDA functions that we will use. Okay, now we want to add an AX plus Y function similar to this one that is running at the moment on the CPU, but now we want to make it a GPU kernel. So I'm just going to copy it here. Oops. Here. I just copied and pasted so that it's twice. So I don't want to destroy the one that I have up here. So I'm going to write a second version. Let me just change the comment here so that it says what it means, what it does. And remember, you add this decorator here, global, so that the compiler knows that this should be compiled as a GPU kernel. And because this cannot have the same name as the previous one, I'll just rename it to GPU AXPY. And the GPU doesn't know anything about OpenMP, so I just keep it like this. Okay, so this program now will run, this function now will run, can run, not will, can run if I, invoke it correctly, it will be compiled and can run on the GPU. But the problem is that I need to pass to it pointers to memory on the GPU, right? So I still need to do some work to do that. So first, what I will do is, I have this function here that allocates memory on the CPU. All it does it calls malloc, which is the system function, the C function that gives you memory on the CPU, and it checks the return result of malloc, and if there was a problem, which means that if the pointer is null, then it gives you an error. Otherwise, it returns it back to the main function. And I have I want to write a similar program for the GPU, which is just this GPU alloc function here. And if you look at what this is doing, it's doing similar things to the CPU allocation function. So it's calling CUDA malloc and then checking if this was successful. And if it was successful, it will just go through this if statement. If it wasn't successful, then it'll print something over the error and then exit, okay? So that's all this does. But what it does is it gives me a pointer on the GPU, okay. Okay, so now we're ready to go and actually do the real stuff in this main program. So this is the bit that is running on the CPU here, the first invocation. I don't want to touch that. What I do want to do is go on here to B and change this so that this runs on the GPU. So the first thing we want to do is, before we can actually call the kernel here, right, is we want to allocate memory on the GPU and copy X1 and Y1 to the GPU before we actually call the kernel. Okay, so that's the steps we want to do here. So I have here some instructions of what you need to do, but first we need to, this is allocating X and Y on the GPU. And before I forget, I will go to the end of this block and free these so that I'm sure that when this ends, they are freed. Okay, so this is just allocating the right amount of memory on the GPU, and it's returning it to a pointer, which is commonly is common practice to prepend with a D underscore, just to make sure that we remember that this is a pointer now pointing to GPU memory, right? This means nothing on the CPU. It only means something inside the CUDA kernel, because that's where this pointer is pointing to memory that's allocated on the GPU. Okay. And then once this data is allocated, we can transfer X1 to the memory that was allocated and was returned to DX, and Y1 to the space that was allocated and assigned DY. So now we've moved the data after these two commands complete. We have X1 in DX and Y1 in DY. So now the data is on the GPU, and now we're ready to call our kernel. Okay, so this AXPY is the CPU function. So what we need to do is call the GPU function, which we named GPU underscore AXPY. And now we need to specify the threads and the blocks, right? And for the meantime, let's just do one thread, one block, one thread per block. This will not be particularly good, but this is what we will start with. Okay, and then the last thing is to, once the program is done, we need to move the data back to the CPU so that this comparison with the CPU version is carried out. Now, this stuff here you can keep it, but it will be misleading, because we should change this print statement so that it prints the performance, so that it indicates this is actually the GPU version, right? So that it's not misleading, and the threads here don't really mean anything. So let's just delete that, and okay. And remove this. Okay. Like that. Okay, so now we should have a GPU version, maybe not the most optimal GPU version, but this should compile and run on the GPU now. Let's see what we get. Okay, that compiled. Let's see if it runs. Okay, so it ran. It gave me something similar for the CPU. And for the GPU, it gave me something astronomical. So this is obviously wrong. And I sort of tricked you into getting this what I'm saying here is that the performance is extremely high, right? So the peak performance of the GPU is like 900 gigabytes per second. And here we're getting something that is like, 10 times, more than 10 times larger. So what's going on here is, and what you should remember is that when you call this GPU function, then this returns immediately, okay? It's not waiting for the kernel to finish before it comes back. So this is a way, this is a feature basically that allows you to run asynchronously things on the GPU while doing other things on the CPU, okay? So when you call GPU AXP, it's not waiting until it's done the vector operation that we wanted to do before coming back to the CPU. It comes back immediately, even if the GPU is doing the processing. So if I want an accurate timing of how long this line took, then I need to synchronize here, right? I need to add a command here, which says, don't continue after this line unless all the GPU kernels are finished. Okay, so this will give us an accurate timing of the GPU kernel. Compile again, and then I'll run again, and this time I should get a more reasonable time. Okay, all right. So this difference is machine precision, 10 to the minus 15, meaning that the calculation should be okay. It's not going to be exactly 0 because the order of operations, etc., on the GPU might be different, but it's machine precision, so that's okay. And let's see what this says, that on the CPU, this took 0.0088 seconds to run. And on the GPU, it took 3.5 seconds to run. So we're doing much worse on the GPU. And the reason we're doing much worse on the GPU is because we only used one thread on the GPU, right? And the parallelism, the performance on the GPU comes from the parallelism. So what can we do? Come on. What can we do to change this? Well, here, right, is where I said, let's just put 1 and 1 for now and worry about this later. So this is where we specify that we want to use more threads than 1 on the GPU. And let me just go to my slides so that I see what I put. Yes, so let's use 1 block for the meantime and 512 threads per block. Okay, so now this kernel will be invoked by 512 threads. Okay, that's good enough. But the problem is that if I go up here and remind myself, what exactly did I say here to do? So this loop is still going to go from 0 to n. So there's no magic here where this loop is going to be distributed over these 512 threads. You have to do that, okay? You have to implement that. So if I keep it as it is, then all you're going to manage to do is have 512 threads doing the same loop, which is pointless, right? We haven't really used the processes in a good way. What you want to do is split this n into 512 pieces and have each piece be different and run on a different thread, right? Okay, so one way to do that is we get, well, let me just copy this and then I explain it here. So we had this, which I will comment out. And now I put this, and let me go step by step and explain to you and maybe see with you. Okay, so thread idx.x. Remember, we only have one block. So this now will be a number from 0 to 511. Okay? So that I thread is just the number from 0 to 511. N thread is just the number of threads that I have in total, which is 512. And now what I want to do is I want thread 0 to do the operation y0 equals a times x0 plus y0, y1 equals a times x1 plus y1, the same for y2, y3, up until n over 512 elements. Then the next elements, I want them to be done by thread 1. Then the next element, I want the next 500, the next n over 512 elements, I want to do by thread 2. And if you look at this, the way that I wrote this for loop, you should be convinced that this is exactly what is being done here. So LT is the number of elements that each thread should process. Okay, so I just designed this so that this is a multiple of 512, right? If it's not, then you have to do other things. But for now, let's just assume that this is a multiple of 512. And so, yeah, and so, so this loop here for the 0 thread will go from 0 to LT. For the thread with I thread 1, will go from LT to 2LT. For the thread which has I thread 3, it will go from 3LT to 4LT, etc. Okay, so each thread will take one continuous part of the operation. Okay. Mm-hmm. So thread idx.x, as you asked before, is filled by the thread index. Yes? Okay. Now, Y is an array which is n elements long. Okay? And in the iteration here, the starting I depends on I thread. Right? So for thread with I thread 0, I will start from 0, but for the thread with I thread 1, which is the next thread, then this will start from LT. No? Yes, I've arranged it to be, but yeah. Okay. Okay, let me say it like this then. So, okay, so for this specific case where we're using 512 threads, okay? So this, I mean, the sort of mental model that you can sort of use is that this function, right, will be run 512 times in parallel. Each thread will run, each thread of the 512, you got it now, right? And for each one, this thread index is different. Yeah, okay? Okay. So that happens down here when we call it like this. Yeah, here is where the magic happens because we call it here saying that we want to use 512 threads. So this is run 512. Okay. Okay, good questions. Okay, so now I compile this. And then I run. And I should get something which is same result as before. It's faster, right? It's like, what is it, 3 times faster? It's more than 3 times faster. But still much slower than the CPU. And okay, so let's see what's going on. Okay, so this is so this is the first thing you should, I mean, so far maybe, you know, this looks very okay, and if you have ever done multi-threading on a CPU, then this looks fine, or maybe familiar. But this is where it starts getting particular for the GPU, okay? So what we have done is we've distributed the work to the threads in a way that's very common for CPU cores, the way you distribute work to CPU cores, where the CPU is optimized. Maybe you know this, or maybe you just do it because it's the common way it's done. The CPU is optimized for a core when it reads a byte of memory, or 4 bytes of memory or whatever. Usually it reads in a whole cache line, we say, right? So usually it doesn't just read those 4 bytes that you want to read, but it actually looks ahead and reads multiple bytes of data after that, some multiple of 2, some power of 2, like 512 or something like this, right? So for the CPU, it's optimal that in the next iteration, right, you just go to the next element in the array, right? And so each core, usually it's optimal to give each core a continuous block of memory to process, okay? This is exactly what you don't want to do on the GPU, just because the memory layout of the GPU is completely different from the CPU. The memory layout on the GPU actually needs you to do the exact transpose of what I said. So it's more optimal on the GPU if continuous threads take contiguous pieces of memory, right? So if you have thread 0 taking byte 0, then you want thread 1 to take byte 1, okay? That's where the efficiency actually is, because of the way that the layout in which the GPU memory is banked, basically. So we're going to do that. We're going to change the way that we still have 512 threads. We still have 1 block, but we just want to turn it around so that each, thread 0 takes element 0, thread 1 takes element 1, thread 511 takes element 511, and then you start over from the beginning, and element 512 goes to element 0. So this is what we want to do here in this next step, where we will go to this kernel, and okay, there are multiple ways to program this. Let me just copy paste this and just convince you again that this does what we wanted to do, at least in terms of what I explained before. I'll just comment this. Okay, so this is the new bit that we've put in. And again, iThread is just thread IDX, and thread is just blockdim.x. And now I've changed the loop where I goes from 0 to n, but it jumps by n thread. So in the first iteration, I will be 0. In the second iteration, I will be n thread. In the second iteration, I will be 2 times n thread. Okay, so far so good. And what am I doing here? In the argument of the array, I'm putting I plus I thread. Okay, so in the first iteration, this line will say 0, 0, 0 for thread 0. In the first iteration, this line will say 1, 1, 1 for the second thread. in the first iteration, this line will say 222 for the third thread, right? And then in the second iteration, remember, I will increment by n thread. So I will be n thread. So in the second iteration, for the first thread, this will say n thread, n thread, n thread. For the next thread, this will say n thread plus 1, n thread plus 1, n thread plus 1, etc. Okay, so I implementing this schedule rather than the previous one. Okay, and I claim this will make a big difference. Let's see, because of what I said, the layout of the GPU, blah blah blah. Now is where I put my money where my mouth is, and indeed you get something which is more than 3 times faster. Okay, so we went from using one GPU thread where it took 3.5 seconds. Then we used 512 threads. It didn't get 512 times better, but it got 4 times better. And then we, using the same number of threads now, but we just changed the order in which we access the data with the thread. So it's the same number of threads, right? So all the improvement here is just memory access pattern, right? And we got something which is, this is 3 times better. Okay, now, what do we do now? What's the next step? I mean, this performance is getting closer to the CPU, but it's still poor. So the next step is the last step. Okay, so so we're only using one block and 512 threads. Let's use as many blocks as we can possibly use, right? So what does it mean to use as many blocks as we can possibly use? I told you it was a bit fast, but when I was introducing, I said you have an upper limit to the number of threads per block, which is 1024. But for all practical purposes, the number of blocks is infinite. It's something like 2 to the 19. It doesn't really, you don't worry about the number of blocks. So how many blocks can I practically use here? As many as I need to have one thread processing one element of the array. So that's basically the maximum I can use, right? So what do I mean by this? If I go down here, so, and okay, let's do this. N thread equals 512 and put 512 and put n thread here. So I just changed it to a variable. Okay, but now let's do this. N over n thread blocks. Okay, so the number of blocks times the number of threads is now the number of elements in the array. And I can allocate one thread to each element of this huge, big array that I'm processing, okay? What does that mean? It means that if I get the global index, so let me comment this out again, like this, comment region, okay. So what does this mean? So if I get the global index, like I explained to you before, so let me do this. Let me copy those 2 lines. Oops. Oh. What am I doing? No. Okay. Sorry. Yeah. So I have those 2 lines, and now I have a new actually, let me just new variable, which is excuse me, new variable which is the block index. Okay. Sorry for jumping around all the time. Okay, so now I have this I thread. This goes from 0 to 511. The number of threads is 512. This is known. But now I also have the block index, which goes from 0 to
the number of blocks I have minus 1. Okay, and now I'm going to do this trick that I was explaining there. Do this, you know, just calculate the global index. So this I now will be I thread plus I block times n thread. So this now is a number. I is a number from 0 to n minus 1, right? So there's one-to-one correspondence between threads and elements of the array. So now I don't need a loop. I can just do that equals a times xi plus yi. The loop has disappeared because I have as many threads as I have elements in the array. And this is a very common paradigm when you program using GPUs. Because you effectively have as many blocks as you need, then you do it this way and let the GPU worry about how to organize the blocks, okay? The GPU does not have this many number of threads. It has less threads, right? So there's not enough hardware to run all of this in parallel. But what it will do, what the GPU will do, is it will run each block, the threads inside each block in parallel, and then some of the blocks will run in parallel, others will be serialized, but it will take care of scheduling the different blocks one after the other or in parallel in order to do this, right? And so now you've eliminated the loop, and let's see. Okay, now if I run this, okay. So this is basically given me now something which I can claim is sort of faster than the CPU. So it takes 0.009 seconds to run on the CPU, 0.001 second to run on the GPU. And the memory bandwidth of the GPU, I had it in a previous slide, is like 900 gigabytes per second. So I'm sort of close to this upper bound, right? So the fastest I could expect this number to be is 900. Maybe you can get close to it, like 750 or something like that, but don't expect to get, you know, much more closer to that. So this is more or less as good as I can get of a performance for this simple operation on the GPU. And remember what did the biggest impact was, first, that I used as many threads as I had elements, right? The last step was the one that had the most impact. But remember, the other thing that gave me the impact was to change this memory layout, the memory order, so that I have continuous threads access continuous elements of the array, right? Okay, so that was sort of the shortish introduction to GPU programming. As I said, the main points covered here was allocating memory, the offload model, launching kernels on the GPU, and this memory access pattern that was important to get the performance. What I didn't cover, and should be sort of, if you want to get serious with GPU programming, is something that you need to worry about, is how to share memory between threads, and also some aspects of thread scheduling, like synchronizing, and when you use like if statements, etc., inside kernels, there's some care to be taken. But hopefully these are things that we could be able to cover in a follow-up training session if there's interest for this. Okay, so that's all I wanted to say today. Sorry for exceeding our allocated time, and I hope this was useful, and I'm happy to take any questions. Yeah. Here I mean physical course. Yeah. Yeah. I
So what I want it to be is physical course, okay? But Slurm has surprised me. I think that means, hopefully that means physical course. There's ways to find that out, but yes. But the intention there was to use physical course. Other questions? Okay. So I think we will ask for some feedback from you, which we want you to be, first of all, we would appreciate if you were honest about, right? Was this useful, etc. And then we will give you some options, I think, for future trainings that will build on this or not, right? So whether you want to see something different, whether you want to see similar things but a bit more advanced, etc. So we'll give you some options. So please, when you receive that, please try to be honest about, about how you found this training and what you would like to see in the future, and we'll try to, obviously if we get 10 different responses, then we'll have to sort of prioritize some. But if there's a consensus about some kind of training that you would like to see, then we can sort of, accommodate that. Okay. All right. Okay. So I can take questions also offline if you want. But thanks. Okay. Thanks.